Okay, just we can classify the errors in the GPS measurement in this the classification. Of course, we can change the classification, but we can classify the errors in instrumental errors, modeling error, measurements errors. So it means the errors that we can control when we are in the field, or processing error. When we have collected data and we want to obtain by our measure, phase measurement, for instance, the positioning. Okay, we start from instrumental errors. We have already seen in the previous lesson that there is an empirical rule that gives us an idea of the theoretical errors that we can have with the GPS signal. We have seen that with the phase measurement we have a higher precision, millimetric precision, because there is an empirical rule that says that we have an error of 1–2% of the wavelength. I remember you that the carry L1 has a wavelength of 19 centimeters and carry 2 have L2 have an error, a wavelength of 24 centimeters. Okay, so this is one of the reason why we are using phase measurement, even if we have problem with the definition of the initial ambiguity, the unknown number of integer cycle between the satellite and the receiver. At the moment that we switch on our receiver and we track the satellite, we don't know this quantity, we are going to estimate, but we can obtain a higher precision. This, of course, if you remember, we have seen that to estimate the ambiguity, we need more measurement. It's not used for real-time positioning. Now there are some kind of applications that we can try to use this measurement or also for real-time application, but it's not important now. With the carry to estimate the initial ambiguity, we need more time, more epoch. So it's not the best signal observation for real-time positioning. The other type of error that we can have a modeling error, and we have different errors. It depends on if we are using code of phase measurement, or if we are using just phase. We can have clock biases, orbit biases, atmospheric biases, or phase measurement or error for phase measurements due to initial ambiguity of the carry or phase center variation. Okay, with biases it means a systematic error in our measurements or a big error in our measurements. So we have already seen that we need a synchronization of time between the clock of the satellite, the clock of the receiver, and the master stations that give us our theoretical GPS time. And the problem is synchronize the receiver and the satellite time. And we have seen that the quality of these two type of clocks is really different. So we have to introduce an unknown parameters that we are going to estimate to synchronize our observation with our time with the time of the satellite. Modeling error. We have seen that we are going to measure the distance between satellite and receiver. This is our measure. And we know in our equation, we introduce the coordinates of the satellite and the coordinates of the receiver in the geocenter reference system. Okay, in this computation, we have supposed to know the position of the satellite, and we really know the position of the satellite, because we have seen that the GPS signal has been modulated by the D code, the D message, and this part of the message, there are the ephemerides, the parameters that give us the position of the satellite. But these are predicted values. Okay, these are predicted values. These are called broadcast ephemerides, transmitted by satellite for real-time positioning. These satellite positioning are computed by the control network, the master station, and are predicted values, are not the real values of the position of the satellite in the space. For the reason that I've written here, the orbit is perturbed by a lot of things, by the motion of the satellite is perturbed by the Earth's gravity field, the attraction of the moon and the sun, the solar radio pressure, and so on. And we have also to take into account, this is the motion of the satellite, and we have also the motion of the Earth, that could be irregular rotation of the Earth. We have to take into account for solid Earth tides, and loading due to ocean, atmosphere, and so on. So it's difficult to predict the real position of the satellite for this reason. So in this slide I put this because in the last year some student was interested in the equation. So this is the equation of the motion of the satellite. This is in a simplified way. On this satellite there are some perturbing force that are due to the atmospheric drag, the direct and indirect solar radiation pressure. Stop me if you don't know some of these effects, due to the magnetic field of the Earth and so on. So we have to introduce this term, and the position of the satellite at a given time t is given by this quantity. Can be expressed in terms of 6 Kepler elements. Okay, and in the figure, next figure, I put a plot by the NASA government that there are the definition of the 6 parameters that give us the position of the satellite. Okay, so we needed to have this quantity to define the position of the satellite, and we can find this information in the broadcast ephemerides that are transmitted by the satellite using the decode or the D message. Or for high precise application, we need to really know the position of the satellite in the sky, really, with a high precision. So in 1992, it started a service called International GNS Service. At the beginning it was called International GPS Service, and one of the services of this of IGS was to compute the ephemerity of the satellite using the real data. So the IGS is given by a network of GPS stations that are observing all the time, 20 hours a day. And these are permanent stations, fixed station, well distributed all over the world. They process the data not to know the position of the point, but to invert, to have the position of the satellite. So there are different research groups that analyze this data. Are called analyze center, and all these different solutions are combined to have what we call precise ephemerides. And this is the slide that we can find in the IGS website, if I remember, is www.igs.org website. This could be the address, sometimes change, but otherwise you can write in the website International GNS Service and you arrive to the website of this service. And these are probably the precision are improved. I didn't check if they update this table, but these are all the products that they have. These are the broadcast ephemerides, because probably if you want to check how many satellites will be in a given place on the Earth at a given time, is a planning, it's called planning phase. You can use the broadcast file and find the position of the satellite. There is also other product with increasing precision up to arrive to the final product, the final ephemerides that give us the position of the satellite, but not in real time. We have to collect data, to 1 week of data, to analyze the data by different centers and combine this to have a final solution. To do this, they take about 12-15 days. So you cannot use this for real-time application. So for some of the for the physical application, like seismic tectonic study or study related to the seismic cycle, for instance, of the fault or something like this, it's not so important to have a real-time solution. We can wait this time to have final solution, the most precise solution. In other applications that are important for the hazard, for instance, it's better to use a good quality of the ephemerides, but in few times, for instance, for the tsunami hazard and so on. And so they produce different products, ultra rapid, predicted half, observed half. It depends on how many observations you are using and how many predicted values are you combining. But you can have this, the first one in real time, the second one in a few hours, or you can have also rapid orbit products in 1-2 days, more or less. And these are the centers that analyze the data, and all the solutions are combined to have the final product. This is a whole table. Probably we can check if you can check if there is some changing in this in terms of precision, in terms of you can see the precision is increasing, or in terms of delay when these values are available, and so on. Okay, this is an example of SP3 file. The file called name of file point SP3 .sp3, sorry, are the file where we can find the final ephemerides. And you can see in this is important, this the first line, because we have information, of course, about the time, year, month and day, but especially for the reference frame, because we have seen that for the positioning we have to define a reference system and a reference frame. A reference frame is the materialization of a reference system. When we have seen that with the GPS we are going to measure the distance between satellite and receiver, and we are going to fix more or less. We are going to see next when we speak about GPS processing software that there are some differences, but now we can see that we can fix the position of the satellite and we obtain the position of the receiver. So it's important that the position of the satellite are determined in a well-defined reference frame, because our coordinates of the point on the earth are related to these coordinates, to this reference frame. So you can find this information in the first row of this file. That is an ASCII file. And there are some information, final orbit combination, obtaining, computing, and a weighted average from all these analysis center. This is for Bern in Switzerland, ESA, GFZ in Germany, JPL in the United States, MIT in the United States, and so on. And these are the position, satellite position of the satellite of the satellites. And we have also information about the clock of the satellite, because we have also to synchronize the clock of the satellite. It's a second order problem with respect to the synchronization of with respect to the clock of the receiver. But we have also this information in this file. Okay, you can use this file, and you can put. There are other information that we are going to see in the during this lesson about phase center variation, ocean loading model. We are going to see it after. And this file can be used by any GPS data processing softwares. So, do you remember all the files that are .sp3? Okay. We can have orbit biases. We have seen it depends on the motion of the satellite and the motion of the Earth. One important motion that we have to take into account is the effect of the shear loading. Okay, we know that due to the attraction of the moon and the sun, on the Earth we have tides of the ocean, and this tide has an effect on the Earth, because the Earth is not a rigid body but is elastic, body. So we have a different distribution, distribution of the masses of the Earth. And we have to take into account also for this effect. In these websites, I checked because in the past was another address. This is a website of OMSALA Space Observatory in the north of Europe. They give us the information to compute this effect and to correct our data. So they produce map of, yes.
How the ocean loading of this tiles changes the era or era?
Sorry, I forgot to switch. Sorry. Okay, I forgot to start again. Okay, so but it's important when you purchase the GPS data to take into account for this and provide the model to the software. And, okay. Anna is a mistake. No, sorry. Sorry, this is a note for me. Sorry, it's in the file, but it was just a note for me. Okay. When you go to this website, we found a lot of information. It's interesting about the physics of the problem, and it's an interactive website. You are going to select ocean tide model. We have a long list of ocean tide models. Some one are old model, other one are new model. Usually for GPS we use this one. Why? I don't know exactly why we use this one. All the software say invited use to use this one. Probably we have to check in the literature the reason of this of using this one. And when you have a GPS data software, this software has been of course tested by the developer, and so they try different model and give you some information. You have to select what type of loading phenomenon do you consider, vertical or horizontal displacement of the effect in terms of gravity. And okay, using green function, you can use elastic model of the Earth, so this elastic model of the Earth is say under construction, so it's not now it's not available. And okay, this is about the center mass information about the center mass of the center of the figure of the Earth. And okay, this usually the most common option are already selected in this page. Okay, the output format, usually we use a BLQ format, is the most used for instance the Bernese software, that is one of the most important scientific processing, data processing software. And you can put all your station here below, put in the name of station and the coordinate. You can use X, Y, Z, or longitude, latitude, and height, and you pass all this information, you copy this information, put here, and you press a button, and you have to fill a field with your email address, and you receive a file in the, for instance, BLQ format. And this can be used. When we have to do this, when you set up a new GPS network, you have to provide this information. Okay, this information gives you a model of the tide, but it's a static model, so it means that you don't have to check to update this file every day or every month and so on, as you have to do for the orbit. Is a model that is a global model and with performing in harmonics and give you information that are static. So when you have a new station, you provide this information for each station, and you can use this all the time when up to you want to change a model. If for some reason you think that a new ocean loading model is better, you can change the file, but you don't have to update this file every often. Okay. This is some information. For instance, these are some of the ocean loading model, and the colored area are missing the ocean tide models. So, for instance, this model, they didn't consider the Mediterranean. So it means that if you are working in South America, probably you can use this model without any problem, if the only problem with this model is this area. But if you have station in Italy, probably this is not an accurate model for Italy, and so on. It's just to give you some differences between one model to another one. Okay. But when I put the website, I invited you to visit the website, and you find a lot of information about the station, about the techniques that are using, the theory, and so on. Okay, so we have seen that sorry, I remember a slide, but probably I removed this slide, or I put in another part of the presentation. I don't remember. Okay, so concerning the modeling errors, we already see clock biases, orbit biases. Now we are going to see another important class of biases. The biases due to the atmospheric biases due to the atmosphere of the Earth. We have different type of the signal coming to us from satellites that are very far from us, 20,000 kilometers far from us. And so the signal goes through the atmosphere and through the space. And we have different effects. Okay, we have some effect due to the rebending, to the propagation with respect to a real space, not a vacuum space. We have effect due to the ionosphere, a layer of the atmosphere, and due to the troposphere, another layer of the atmosphere. We are going to see this different type of effect. Okay. Our signal, we are going to measure the distance. So in the equation that we have written is just the Eulerian distance between one point to another point, satellite and receiver. But we have about a straight line connecting satellite and receiver. But you know that for instance, we are using electromagnetic wave, and the electromagnetic wave has a velocity given by the velocity of the light if you are in the vacuum. But we are in the atmosphere, and so we have a refractive index, and the velocity is not the velocity of the height. We have to take into account for this refractivity index. And moreover, we know that for the Fermat principle, electromagnetic wave follow the shorter path in terms of time. So when we have to compute the distance between satellite and receiver, we are going to integrate this expression. And in the vacuum, if we consider a case where the refractive index is equal to 1, that is the velocity of propagation is equal to the velocity of the light, we have the geometric distance in the vacuum. We call S0. It's like a reference. So the differences between the previous S and S0 give us the error due to the refractivity, due to the atmosphere. We are not in a vacuum. Okay. This is a physics. I know that you already know this quantity, but this effect. But we have to take it into account also for the GPS. This is a simple part. We can predict this error, and there are models and so on. Okay. About the ray bending effect, it depends on the elevation angle of the satellite. The elevation angle is the angle between the horizontal line, this is the GPS receiver, and the satellite. This angle is called elevation. This is the azimuth angle with respect to the vertical. So this type of effect increase when we are using a satellite low with respect to the horizontal, so with low elevation angle. Okay, you can see that when the elevation angle is small here, when satellite is low, we have a bigger effect, because it is bigger the path along the atmosphere. Okay, so often we can cut the observation at a low elevation angle. This was really done in the past. Now we try to use all the observation, also observation very low, because we are going to see that we need this observation when we use GPS for high precise application. Okay, this is just a slide about the layers of the atmosphere. So we have the Earth, we have troposphere, tropopause, stratosphere, ozone layer, this red line, mesosphere, and ionosphere. So we have seen my presentation that we are going to talk about troposphere error and ionosphere error. So these two layers are the most important layer for GPS measurement. The troposphere layer is the layer where we are living, okay, up to 14 kilometers. The ionosphere is quite far, and you know the ionosphere is very important for radio transmission. And we are going to see that these two layers have two different effects on the GPS signals. Okay, we started from the ionosphere. Okay, the ionosphere. We have a lot of atoms have ion, and because there are dissociation of the atom, so it's a very with a lot of ion, positive and negative ion. And the important thing is that the ionosphere is a dispersive layer medium for the GPS signal. What is a dispersive medium? It means that the velocity of propagation of the signals is changing related to its frequency. Do you know? So we are going to, we have it depends the velocity of the electromagnetic wave depends on its frequency in this type of dispersive medium, and the GPS frequency used that is the radio waves in L band have this effect. The ionosphere is a dispersive medium for this frequency. So we can compute again the differences in the paths due to this layer. This is without dispersive medium, and this with the dispersive medium. And this is the relationship of the equation of the delay, more in force approximation. It depends on the frequency of the signal. C is a constant, and it depends on NE, on the density of electron present in the ionosphere. So we have different effects if you change the sign. The equation is the same, but change the signs. For the code measurement, you see P means pseudo range, the distances obtained by code, by time measurement, or if you use phase. The equation is the same, we have a change in the sign. And so what we can see is an important thing that, okay, it depends on the frequency. So in the GPS we have at the moment 2 carries. In Galileo we already have 3 carries, but we are going to see. So GPS were set up, were designed using 2 frequencies, 2 carries. And this is the reason. Because we know that the ionosphere is a dispersive medium from radio waves in this band. So the people know that we have an effect on our measure, and to control the effect, they design to put 2 carries, 2 frequencies. So we have 2 different effects because it depends on the frequency. We have an effect for L1 and an effect for L2, for the 2 carry. And another important thing that is dependent on this quantity, the density of the electron in the ionosphere. But do you think that it is easy to obtain this information, to know how many electrons we have in the ionosphere? No, because it's really time dependent. It's changed by the day and by the night. It depends by the sun activities. So it's not easy to have this a priori information on the contents of the electrons. Okay, the magnitude of this disturb is of the order of some centimeters to some meters. But, okay. Oh, this is, I obtained the formula that we have seen before, okay. This is important that this approximation is true at the first order. So it means that it is not the really definition. We have to take into account also for other terms to have a more precise definition of the ionosphere delay, but in many applications it's sufficient this first order. We have problem. Okay, this is what we already say, that the GPS has been designed with the 2 frequencies just to take into account for this error. So we are going to see what we can do if we have 2 frequencies, 2 carries. We can combine this observation and find a combination called iono-free combination that reduces the ionospheric error in our observation. It means that, for instance, here we have P code observation, and here I put phase observation, but it's not a problem, it's just we have seen with different insights. Okay, this is the observation, the pseudo-range observation obtained by code for L1, and this for L2. Of course, we have put the distance, the theoretical distance between satellite and distance and receiver, the clock errors that are important, and the ionosphere. At the moment, we forgot other errors. For instance, the orbit error. We focalized just on the ionosphere. And if we combine these two observations in a linear combination, we can try to find some coefficient N1 and N2 that reduce this effect, that we can cancel this effect. So this combination is called iono-free. So it's a new observation. It's like if you have another carry, okay, it's not a real carry. We obtain in combining two observations in our receiver or in our software, in our software. We combine observation, other observation, and if the coefficient N1 and N2 are given by this relationship related to the frequency, we obtain a new observation, L3, that is not affected by the ionospheric delay. This is true at the first order, because we have seen that this is true if we use the equations that we have seen before, where we have C over the frequency square multiply for the integral of the electronic content. Okay, this was an equation that was given at the first order. So this combination is free by the ionospheric delay at first order.
Can I ask a question?
Yes.
I don't understand if you talk about two different observations of the comparison between the two frequencies on the signal.
We have two signals in GPS simultaneously. We have two carry with a different wavelengths and different frequencies.
Compare these two signals in.
Yes, we combine. No, because often the students say we compare. No, it's a combination.
Okay.
Compare, I see just that the delay is different, but this not change, cancel the differences. The combination using this type of combinations using N1 L2 that give us these values, give us a new observation that are free from this effect. It's like a strategy in your processing.
Differential approach or something like
It's
that.
not a differential approach in this case. It's a combinational approach. We are going to see differential approach to remove some type of error. In this case, it's just a combination. We can use this combination in a differential approach. We are going to see, but at the moment, it's just a combination. It means that I have one receiver, I can compute this observation just from one receiver. And this observation is free from the first order. I'm underlying often at the first order. Why? Because we have seen that during very high sun activity, solar activity, this approximation is not sufficient. We have to take into account for high degree, and this is the reason that the new global navigation satellite system are designed to have 3 carries, not just 2, because during some period with very high solar activity, 2 frequencies are not sufficient. And also because there are improvement the study of the ionosphere using GPS data. So they need to have higher information, higher order information on the ionosphere. Sorry. Okay. To an exercise at home is very easy. I think that you can do it. You can demonstrate that the ionosphere observation L3 is not affected by the ionosphere disturb. So you have just to find N1 and N2, the 2 coefficients in the coefficient. Of course, we have seen 3-1 equation, the first one with C over frequency square and so on. So it's just a joke, it's just a simple exercise to see how we obtain the ionosphere combination. Okay. Okay, when the solar activity is very intense, we need, there is a video, but probably we have the problem, I forgot.